The cosmos rarely sends gifts, and never without a price. Yet in the span of a heartbeat, not one but two interstellar strangers have slipped into our celestial backyard. The story of 3I-ATLAS was barely unfolding when, on November the 3rd, another visitor appeared, C/2025 V1 Borisov, quietly flagged by the same sharp-eyed Crimean astronomer who once revealed 2I Borisov to the world. And this newcomer has chosen a position that feels deliberate, settling between Atlas and Earth, as though guarding the path, or studying its destination. It's the kind of alignment you'd expect from a careful architect, not the chaotic ballet of celestial mechanics. So what is this? Chance, or choreography? Stay with me until the end as we trace the hidden pattern of these arrivals, and unravel why this moment feels less like coincidence, and more like a message etched in cold starlight, one none of us is ready for. If these mysteries have you hooked the way they have me, make sure to hit like and subscribe so you don't miss a single update as this unfolds in real time. Drop a comment with where you're tuning in from, what time it is there, and what you think about the new visitor. And if you want to help this community grow, share this video on X, Facebook, Reddit, or even just in your group chats. You're the reason we can keep chasing stories like this, so thank you for having our back. Part 1. The Interstellar Alignment. No one expected. On November the 3rd, 2025, something appeared in the sky that shouldn't be there. An astronomer in Crimea, working through the cold pre-dawn hours with his modest telescope, registered a faint smudge of light moving against the background stars. Within hours, the object received its official designation, C/2025 V1 Borisov. The name alone should make you pause, because the man who found it, Gennady Borisov, is the same person who discovered 2I/Borisov back in 2019, only the second confirmed interstellar object in human history. Lightning doesn't usually strike twice in astronomy. When it does, people start asking questions. Here's where things get interesting, and by interesting I mean unsettling in a way that makes professional astronomers choose their words very carefully. This new object isn't just wandering through our solar system on some random path. It's positioned directly between Earth and another visitor from beyond our solar system, 3I-ATLAS, an object discovered just months earlier that's already raising eyebrows across the scientific community. Imagine looking up at the night sky and seeing two airplanes, one closer to you, one farther away, and the moon sitting perfectly between them from your perspective. That's a line of sight alignment. It happens. But when those airplanes are actually interstellar objects, each travelling millions of miles through the void, and they just happen to line up with Earth at this particular moment in cosmic history, the coincidence starts to feel a little too convenient. Let me clarify what we mean by between, because this matters more than you might think. When astronomers say one object appears between two others, they're usually talking about line of sight, a projection effect. You're standing on Earth, looking out into space, and from your vantage point, Object A appears to sit between you and Object B. But space is three-dimensional, maddeningly so. Those objects could be separated by vast distances in actual physical space, millions of miles apart in depth, and you'd never know it from their positions on the sky. It's like looking at a photograph of a landscape where a nearby fence post appears to touch a distant mountain. They're not actually touching, they're just aligned from the camera's perspective. But here's the thing that's keeping some researchers awake at night. The discovery of C/2025 V1 didn't come from some massive automated survey with thousands of telescopes scanning every square degree of sky. It came from one person, using relatively modest equipment, who happened to be checking a very specific region. And that region, according to researchers who've been quietly crunching the numbers, overlaps significantly with the projected path of 3I-ATLAS. When someone on a scientific forum first noted this alignment, they didn't make a big announcement. They posted a cryptic observation about ephemerides, the predicted positions of celestial objects, showing an unexpected convergence. No headlines, no press release. Just a quiet note that said, essentially, this is odd. The value of this alignment, if it holds up under scrutiny, cannot be overstated. We have confirmed exactly 3 interstellar objects in all of human history. 1. Apostrophe Oumuamua in 2017. 2. 2I/Borisov in 2019. 3. 3I-ATLAS in July of 2025. Now we have a 4th candidate, and it's showing up in the same general corridor as number 3, discovered by the same person who found number 2, appearing at a time when number 3 is making its closest approach to our planet. The odds of this being pure coincidence are not zero, but they're uncomfortable enough that even conservative scientists are starting to use phrases like statistically noteworthy and warrants further investigation, which in astronomy speak means something has rattled them. Think about what this implies if the alignment is more than projection. If these two objects are actually travelling along similar paths through three-dimensional space, not just appearing aligned from our viewpoint, then we're looking at the first confirmed case of multiple interstellar visitors arriving in our solar system along a shared trajectory. That suggests a source, a direction, a corridor through the galaxy where objects are being funneled, either by gravity, by stellar dynamics, or by something we haven't even considered yet. It means the universe might be less random than we assumed. It means there could be patterns to how these things arrive, and patterns mean predictability, and predictability means we might be able to anticipate what's coming next. Or, and this is the thought that probably shouldn't be spoken out loud, but I'm going to say it anyway, it means something else entirely. Because if you were an intelligence from another star system, and you wanted to send something to observe a particular solar system without drawing too much attention, you might send it along a path that looks natural, that mimics the trajectory of ordinary interstellar debris. And if you wanted to send more than one object, perhaps a probe and a relay, or a scout and a collector, you'd probably send them along the same corridor for efficiency. You'd position them so one could observe while the other remained inconspicuous. You'd place one, say, directly between the target planet and the other object, where it could triangulate, communicate, or simply watch. I'm not saying that's what's happening. I'm saying that's the question now sitting in the back of some very smart people's minds. The question they won't voice in peer-reviewed journals but will whisper about over drinks at conferences. Because the universe has just handed us a puzzle that doesn't fit neatly into the box labelled random cosmic coincidence. And once you notice the edges don't line up, you can't unsee it. The discovery of C/2025 V1 might be the beginning of something we don't have a name for yet. Or it might be nothing. But right now, in early November of 2025, we're standing at a threshold, looking up at two visitors from beyond and wondering if they're travelling alone. Part 2, why astronomers are quietly nervous. Let's start with what we know for certain about 3I-ATLAS, because this object has been strange from the moment it appeared. On July 1st, 2025, the Asteroid Terrestrial Impact Last Alert System, mercifully shortened to ATLAS, flagged an object moving through the constellation of Virgo. Within days, orbital calculations confirmed what astronomers simultaneously hoped for and dreaded: a hyperbolic trajectory, with an eccentricity greater than 1. In plain language, that means this thing isn't bound to our Sun. It came from somewhere else, and after its brief visit it's leaving forever. That makes it interstellar, only the third confirmed visitor from beyond our solar system in human history, and the first one we've had a chance to study in detail since 2I/Borisov back in 2019. But 3I-ATLAS didn't behave like a polite houseguest. Most comets, the ones born in our solar system, remain dormant until they get close to the Sun, typically inside Jupiter's orbit. The Sun's heat warms their ices, the ices sublimate into gas, and you get that characteristic coma and tail, the glowing halo and the trailing streamer that make comets so photogenic. 3I-ATLAS said no thank you to that script. It started showing a coma while still well beyond Jupiter, at a distance where sunlight is faint and temperatures are brutally cold. That's not supposed to happen with water ice. Water doesn't sublimate easily out there, so either this object is made of something more volatile, or something else is providing energy. The composition studies made things weirder. Early spectroscopic analysis suggested an unusually high ratio of carbon dioxide to water ice, something like 8:1 in some estimates, which is bizarre. Comets from our solar system tend to be water-dominant, with CO2 as a minor component. This ratio is inverted, suggesting 3I-ATLAS formed in a very different chemical environment, probably around a star with different temperatures and elemental abundances than our Sun. That's exciting because it gives us a window into alien stellar systems, a chance to study chemistry that literally doesn't exist naturally anywhere in our neighbourhood. It's also unsettling because it means this object is profoundly foreign, made of stuff that plays by different rules. Then there's the brightening. Comets typically brighten as they approach the Sun, following a predictable curve based on distance and sublimation rates. 3I-ATLAS brightened faster than models predicted and the brightening showed variations, little jitters and surges that don't fit standard outgassing models. Some researchers noted that these variations occurred around the same time that Borisov discovered C/2025 V1, though correlation is not causation, and we should be careful not to read too much into timing. Still, it's one more item on a growing list of oddities, one more reason why conversations about this object tend to include phrases like, "we're not sure," and "further observations are needed," which is science code for "this doesn't make sense yet." Now enter C/2025 V1, parenthesis Borisov, close parenthesis. Discovered November 2nd or 3rd, depending on your time zone, by Gennady Borisov, the man who discovered 2I/Borisov in 2019. Let me emphasize how unlikely this is. Interstellar objects are rare, vanishingly rare. Before apostrophe Oumuamua in 2017, we had never confirmed a single one in all of human history. The fact that Borisov found 2I/Borisov was extraordinary. The fact that he's now potentially discovered another interstellar candidate 6 years later strains credulity. Either this man is cosmically lucky, or he's looking in the right places for reasons we need to understand, or something else is going on that we haven't grasped yet. The trajectory of C/2025 V1 adds another layer. Without full orbital data, which takes time to accumulate, we can't say definitively whether it's interstellar, but preliminary observations show it entering from a similar region of sky as 3I-ATLAS. Not identical, but close enough that people who spend their lives calculating orbital mechanics are starting to sketch diagrams and mutter about corridors and streams. If both objects are coming from roughly the same direction, that suggests a shared origin point, a stellar system or region that's ejecting material toward us. That's plausible. Stars can shed debris. Giant planets can slingshot smaller bodies into interstellar space. But the timing is tight. Too tight for comfort. Here's a simple table of what we're looking at, stripped to the essentials. 3I-ATLAS, discovered July 1st, 2025. Confirmed hyperbolic orbit, comet activity at large solar distance, composition skewed heavily towards CO2, brightening anomalies, now C/2025 V1, discovered November 2nd or 3rd, 2025, orbital data still preliminary, possible comet activity noted by discoverer, same discoverer as 2I/Borisov, sky position places it between Earth and 3I-ATLAS. The differences are there, sure, but the similarities are enough to make you pause and wonder if we're looking at cousins, siblings, or something even more connected. Coincidence is comfortable. We like coincidence. It lets us file away strange events as flukes, statistical noise, the universe, being random in ways that occasionally look meaningful but aren't. Patterns, on the other hand, patterns are uncomfortable. Patterns imply structure, causation, intent, or at least mechanism. Patterns force us to ask why. And why is a dangerous question because it opens doors we might not be ready to walk through. Right now we're standing in front of one of those doors, and it's starting to creak open. Two interstellar objects, or candidates for interstellar status, appearing in our solar system within months of each other, discovered by individuals paying very close attention to very specific regions of sky, showing behaviours that don't fit comfortably into our existing models. Is it coincidence? Maybe, but maybe is where the interesting stories live. What might link these objects? Keep that question in your mind. Hold it there like a stone in your pocket, something solid and heavy. Because in the next part, we're going to explore 3 scenarios, 3 possible explanations for what we're seeing, and only one of them is boring. Part 3, 3 scenarios, only one is boring. Every good mystery needs suspects, and this one is no different. We have 3 main interpretations for what's happening with 3I-ATLAS and C/2025 V1, 3 ways to explain why these objects are showing up in our solar system at nearly the same time, from similar sky regions raising eyebrows across the astronomical community. One of these scenarios is simple, safe, the kind of explanation that lets everyone sleep soundly. The other 2 are progressively more interesting, and by interesting I mean they crack open possibilities that most scientists would prefer to leave firmly sealed. Let's walk through them one by one, and you can decide which one feels most likely or most unsettling. Scenario 1. Projection coincidence. This is the Occam's razor option, the explanation that requires the fewest assumptions. According to this view, 3I-ATLAS and C/2025 V1 are completely unrelated visitors from entirely different parts of the galaxy, arriving in our solar system by pure chance. They happen to appear aligned from Earth's perspective, but that's just geometry, a trick of viewing angle. Imagine standing on a street corner and seeing a bird flying overhead at the exact moment a plane passes behind it. From your vantage point, they look close, maybe even touching, but in reality they're separated by thousands of feet of altitude. Same principle here. The objects look between from Earth, but in three-dimensional space they might be millions of miles apart in depth, with no physical connection whatsoever. This explanation fits with what we know about interstellar objects. They're rare, but not impossibly rare. Based on detections of apostrophe Oumuamua and 2I/Borisov, astronomers estimate that several interstellar objects probably pass through the inner solar system every year. We just don't see most of them because they're faint fast and our surveys aren't comprehensive enough to catch everything. So maybe we're simply getting better at detecting these things. Maybe Borisov is an exceptionally skilled observer who happens to be looking at the right patches of sky. Maybe the timing is pure luck. This scenario is clean, tidy, and requires no exotic physics or coordination between objects. It's the explanation that most peer-reviewed papers will probably default to, at least initially. But here's the problem with scenario 1, the thing that keeps it from being entirely satisfying. It begs the question, why now? Why are we suddenly detecting multiple interstellar candidates within a few months, after having confirmed only 2 in all of prior human history? You could argue that our detection capabilities have improved, which is true. ATLAS, Pan-STARRS and other survey systems are getting better at spotting faint, fast-moving objects, but the improvement has been gradual, not a sudden leap that would explain a cluster of detections, and there's the matter of the sky position. Even if these objects are unrelated, the fact that they're arriving from similar regions, being spotted by observers who are paying attention to those specific regions, suggests something more than pure randomness. Randomness doesn't usually cluster this way. Scenario 2, 2 independent interstellar objects arriving via a similar corridor or cluster. This is where things get more interesting. Imagine a river in space, a gravitational lane or dynamical pathway that funnels interstellar debris from a particular source toward our solar system. This could happen naturally. Stars eject material all the time. When a giant planet migrates inward in a young stellar system, it can gravitationally slingshot smaller bodies outward at high speed, sending them into interstellar space. If our solar system happens to be downstream from one of these ejection events, we might see multiple objects arriving along similar trajectories, like a swarm of cosmic refugees fleeing the same disaster. This scenario is rare but plausible. It doesn't require any exotic physics or artificial intervention. It just requires that somewhere out there, a star system underwent a violent event, a close stellar encounter, a planetary migration, maybe even a supernova shockwave, and that event scattered material in our direction. The objects would be travelling independently, not bound to each other, but their paths would share a common origin, like 2 bullets fired from the same gun at slightly different times. If this is what's happening, it has enormous implications for astrophysics. It means interstellar space isn't as empty and random as we thought. It means there are streams, flows, corridors where material concentrates, and if we can map those corridors, we might be able to predict when and where the next visitors will arrive. But scenario 2 has its own puzzle. If 3I-ATLAS and C/2025V1 are both part of an ejected cluster, why do they look so different? 3I-ATLAS shows strong coma activity and unusual composition. C/2025V1, based on very preliminary observations, might be showing activity too, but the details are sparse. If they came from the same source, you'd expect some family resemblance, similar chemistry, similar behaviour. Maybe they have that resemblance, and we just haven't collected enough data to see it yet. Or maybe they're from the same region but different subpopulations, like 2 rocks from the same mountain that formed at different depths and under different pressures. Possible, but it requires some fine-tuning of the explanation. Scenario 3, a paired or correlated origin. This is the scenario that most scientists won't say out loud, but that hangs in the air during late-night discussions. What if these objects are connected not just by a shared source region, but by intent or function? What if they're fragments of a binary system, 2 chunks of a parent body that broke apart but stayed loosely associated during their interstellar journey? Or what if, and I'm going to say this clearly and carefully, one of them is natural and the other isn't? What if C/2025 V1 is an artificial probe sent by someone or something to observe 3I-ATLAS as it passes through our solar system, or to observe us as we observe it? I can already hear the objections. There's no evidence for artificial origin, none. The idea is wildly speculative, the kind of thing that gets you laughed out of serious scientific conferences, and those objections are valid. We should not leap to exotic explanations when mundane ones are available. But let's be honest about what we're seeing. Two interstellar objects, arriving in close temporal proximity, from similar sky regions, discovered by individuals who are paying very close attention to those regions, with one object positioned directly between Earth and the other. If you were designing a mission to study an interstellar visitor, or to study a solar system that's watching an interstellar visitor, this is exactly how you'd position your assets. One object draws attention, the other watches quietly from a vantage point that gives it a clear view of both the visitor and the observers. Assessing which scenario fits best requires data we don't fully have yet. Orbital calculations for C/2025 V1 are still preliminary. We need more observations, better astrometry, spectroscopy to determine composition, photometry to track brightness and activity. But based on what we know right now, Scenario 1 feels too convenient. Scenario 2 is plausible and exciting in its own right. Scenario 3 is speculative but tantalizing, the kind of possibility that makes you check the sky a little more often, just in case. The value for you, for anyone following this story, is understanding that these options exist. We're not in a place where we can definitively rule anything out, and that's both thrilling and unnerving. The takeaway here is simple. Scenario 1 is the easy fallback, the default assumption that lets everyone move on with their lives. But something in the data, something in the timing and the positioning and the sheer improbability of lightning striking twice, nudges us toward the more intriguing possibilities. We're not at proof yet. We might never be. But we're at the point where serious people are asking serious questions, and that's where discoveries begin. Next, we're going to dive into why the geometry matters, why the word between is doing so much heavy lifting in this story, and what it might reveal about what's actually happening out there in the dark. Part 4. The positioning problem, why between matters. Geometry is destiny in astronomy. Where an object appears in the sky, how it moves relative to other objects, the angles and distances that separate celestial bodies. All of this tells us stories about mass and motion and gravity, about cause and effect stretching across millions of miles of empty space. But geometry can also lie, or at least mislead, because we're always observing from a single vantage point Earth, and that single perspective collapses three-dimensional space into a two-dimensional projection. What looks close might be far. What looks aligned might be offset by vast distances in the third dimension. This is why the positioning of C/2025 V1 between Earth and 3I-ATLAS matters so much, and why we need to be very careful about what between actually means. Let's start with the basics. When astronomers locate an object in the sky, they use a coordinate system called right ascension and declination, which is basically latitude and longitude projected onto the celestial sphere. Right ascension measures east-west position, declination measures north-south. These coordinates tell you where to point your telescope, but they tell you nothing about distance. An object at 5 million miles and an object at 5 billion miles can have the same right ascension and declination. They're both somewhere along the same line of sight from Earth, but separated by a gulf of space that makes the difference between a neighbour and a stranger. Distance adds the third dimension. Astronomers measure distance in several ways depending on the object. For nearby things like asteroids and comets, you can use radar ranging or parallax, watching how the object shifts position relative to background stars as Earth moves in its orbit. For interstellar objects, you rely on orbital mechanics. If you track an object long enough to define its orbit, you can calculate where it is at any given time, how far from the Sun, how far from Earth. But here's the catch. Early in a discovery, before you've accumulated enough observations, the orbital solution is uncertain. The object could be here, or it could be there, and the error bars are often uncomfortably large. So when we say C/2025 V1 appears between Earth and 3I-ATLAS, we're making a statement based on preliminary data with significant uncertainties. It might truly be between in the sense of occupying the physical space along the line connecting Earth and 3I-ATLAS, sitting in the corridor like a rest stop on a highway. or it might just appear between from our viewing angle, while actually being offset to the side or in depth by distances that render the alignment meaningless. This ambiguity is important because it changes what questions we should ask and what explanations we should consider. Let's explore an analogy. Imagine two ships crossing an ocean at night. From your position on shore, you see the lights of both ships, and at one moment they appear to align perfectly, one directly behind the other. You can't tell how far offshore each ship is, so you don't know if they're close together or miles apart. Then you notice something odd. As the nearer ship moves, its lights dim slightly, just for a moment, as if something passed between you and the ship, blocking part of the light. Now you have reason to suspect the two ships might actually be close in three-dimensional space, that one is occulting or shadowing the other. That dimming event changes your interpretation from possible alignment to probable interaction. This is what astronomers are quietly checking for with 3I-ATLAS and C/2025 V1. Are there any brightness variations in 3I-ATLAS that correlate with the position of C/2025 V1? Is there any evidence of occultation, where one object passes in front of the other from Earth's perspective, causing a temporary dip in light? Is there any spectroscopic signature that suggests material from one object is interacting with material from the other, gases or dust streams crossing paths? So far, publicly available data doesn't show definitive signs of interaction, but the observations are still early and incomplete. Absence of evidence is not evidence of absence, especially when you're looking for subtle effects in faint, distant objects. Now let's talk about past anomalies, because 3I-ATLAS and C/2025 V1 aren't the first interstellar visitors to behave strangely. Apostrophe Oumuamua, the first confirmed interstellar object, showed non-gravitational acceleration, a small but measurable change in velocity that couldn't be explained by the Sun's gravity alone. The leading explanation is outgassing. Even though no coma or tail was detected, the idea being that sublimating ices on the object's surface created a tiny rocket effect. But some researchers, notably Avi Loeb at Harvard, have argued that the acceleration profile doesn't fit standard outgassing models and might indicate something else, possibly artificial propulsion, or an unusual shape that catches solar radiation pressure in unexpected ways. 2I/Borisov also showed oddities. It was more active than expected for its distance from the Sun, and spectroscopic studies revealed unusual abundances of certain gases, suggesting it formed in a chemically distinct environment. These deviations from normal comet behaviour are why interstellar objects generate so much attention. They're not just tourists from other star systems, they're messengers, carrying information about conditions elsewhere in the galaxy, and sometimes that information is written in a language we don't fully understand yet. The question that hangs over this whole discussion is whether one object could be shadowing or occulting the other from Earth's vantage point, not as a random geometric accident, but as a deliberate positioning choice. I want to be very clear here. There is no evidence that either object is artificial, none. But if you were an intelligence sending a probe to study another interstellar object, or to study the reaction of a planetary system to an interstellar visitor, you would want your probe positioned somewhere with a good view. Between the target system and the object of interest is a natural choice. It gives you a line of sight to both, allows for triangulation, and lets you intercept signals or material streaming from one toward the other. What does directly between mean physically? It could mean several things. It could mean simply along the same line of sight, a two-dimensional alignment with no special three-dimensional relationship. It could mean occupying the same corridor in space, travelling along similar trajectories that happen to be aligned with Earth at this moment. Or it could mean positioned intentionally, with one object placed at a specific distance and angle relative to the other to optimize observation, communication, or collection. We don't know which of these is true yet, and until we have better data, we're stuck in a state of productive uncertainty, where multiple explanations remain viable. This geometry, this betweenness, triggers speculation precisely because it increases the chance of interaction, coordinated origin, or at least a shared pathway. If the objects were arriving from opposite sides of the solar system, separated by the Sun's orbit and 1 billion miles of empty space, we'd shrug and say coincidence, two unrelated visitors. But they're not. They're close in time, close in sky position, and potentially close in physical space, and that closeness is the whisper that something might be connected here, something we need to understand. Next, we're going to zoom in on C/2025 V1 itself, because this object has its own set of oddities and they don't fit comfortably into our existing comet models. Part 5. What's odd about C/2025 V1 Borisov? Gennady Borisov is not a household name, but in the world of small body astronomy, he's quietly become a legend. On August 30th, 2019, using a telescope he built himself at the Margot Observatory in Crimea, Borisov spotted a faint object moving through Cassiopeia. Within days, orbital calculations confirmed it was interstellar, only the second such object ever detected, and it was subsequently named 2I/Borisov in his honour. That discovery alone would be the crowning achievement of most astronomers' careers. Finding one interstellar visitor in a lifetime is extraordinary. Finding two starts to look like a pattern, or at least a skill set that demands explanation. On November 2nd or 3rd, 2025, depending on your time zone and which preliminary report you trust, Borisov detected another object. This one received the provisional designation C/2025 V1, with Borisov appended in parentheses as a nod to the discoverer. The C prefix indicates it's being treated as a comet, at least initially, though that classification could change as more data accumulates. The V indicates it was discovered in the first half of November, and the 1 means it was the first such object reported in that period. These designation codes are dry and bureaucratic, but they carry weight. An object gets a C designation when it shows cometary activity, a coma or tail, which means C/2025 V1 was doing something visible when Borisov found it. What do we actually know about this object? Frustratingly little, because it's still in the early observation phase. Discovery details are sparse. The object was detected at a relatively faint magnitude, which means it's either small, far away, or not particularly active compared to bright comets. Borisov noted coma activity in his initial observations, a fuzzy halo around the nucleus suggesting gas or dust emission, but confirming that observation requires follow-up from other telescopes, and that takes time. Astrometric data, the precise measurements of position over time needed to calculate an orbit, are still being collected from multiple observatories. Until we have a well-constrained orbit, we can't say definitively where this object came from, or where it's going. But here's where things get interesting, in the way that makes your spine tingle, and your mind start racing through possibilities. Early reports from amateur astronomers, people who watch the sky obsessively and post their findings on forums and mailing lists, have flagged some oddities about C/2025 V1. I need to emphasise that these are not peer-reviewed findings. They're preliminary, unverified observations from skilled amateurs who are often ahead of the official curve, but also prone to error and overinterpretation. Take what follows with appropriate scepticism, but don't dismiss it entirely, because sometimes the amateurs see things first. First oddity, coma activity at large solar distance. If the initial observations are correct and the object was showing a coma when discovered, that's unusual for a typical comet. Most comets don't start outgassing until they're inside Jupiter's orbit, where solar heating is strong enough to sublimate water ice. If C/2025 V1 is active at a larger distance, it suggests the nucleus contains highly volatile ices like carbon monoxide or carbon dioxide, which sublimate at lower temperatures. That would make it similar to 3I-ATLAS, which also showed early activity, and the similarity is worth noting. Objects that behave alike often share a common origin or formation environment. Second oddity, possible carbon chain depletion. This is highly speculative and based on one amateur spectroscopic observation that might not hold up under professional scrutiny. The observer claimed to detect weaker than expected emission lines from carbon-bearing molecules, particularly C2 and C3, which are common in comet comae. If true, this would suggest an unusual composition, possibly depleted in the organic materials we expect to find in comets. But again, one observation from one amateur is not enough to build a case. We need professional spectroscopy, multiple observations, careful calibration. Until then, it's an interesting note, nothing more. Third oddity, light curve jitter. Several amateur observers tracking C/2025 V1 have reported that its brightness fluctuates on short timescales, hours to days, more than you'd expect from a stable comet nucleus rotating in sunlight. Comets do vary in brightness as they rotate because their shapes are irregular, and different sides reflect different amounts of light. But the variations reported for C/2025 V1 are larger and less periodic than typical rotation curves. Possible explanations include outbursts of gas or dust, a tumbling rotation rather than a stable spin, or a fragmented nucleus with multiple active regions. Or it could be observer error, instrument artifacts, atmospheric effects. We won't know until professional photometry is available. Fourth oddity, and this is the one that's generating the most buzz in certain corners of the internet: transverse acceleration. A few independent trackers, amateurs with good equipment and good software, have noted that C/2025 V1's position is slightly off from where a purely gravitational orbit would predict. The offsets are small, within the noise for most observatories, but consistent across multiple nights. This could indicate non-gravitational acceleration, the same phenomenon seen with apostrophe Oumuamua, caused by outgassing creating a tiny rocket effect. Or it could be measurement error, systematic biases in the astrometry, or just the normal uncertainty you get when tracking a faint object with limited data. Flagged as unverified means exactly that. Don't bet your life on it, but don't ignore it either. Let's step back and ask why any of this matters. C/2025. V1 might be nothing more than an ordinary short-period comet, a chunk of ice and rock from the outer solar system making a routine pass around the Sun. The Borisov name might be coincidence, the result of one man's dedication to scanning the sky night after night until he finds something. The oddities might evaporate under professional scrutiny, revealing themselves as observer error or misinterpretation. That's the most likely outcome, and we should hold it as the baseline expectation. But there's also a chance, small but non-zero, that this object is something more. The behaviour doesn't fit neatly into established comet models. The timing and positioning relative to 3I-ATLAS are uncomfortable. The fact that the same person who discovered an interstellar object 6 years ago just discovered another candidate, appearing in a region of sky that overlaps with the only other confirmed interstellar visitor currently in our system, strains the limits of coincidence. Maybe Borisov is simply that good, that lucky, that dedicated. Or maybe he's looking in the right places because the right places are showing activity, signals, arrivals that others aren't noticing yet. The value of focusing on C/2025 V1 is that it might be the key that unlocks the larger mystery. If this object turns out to be interstellar, if its orbit is hyperbolic like 3I-ATLAS, then we're not looking at two isolated visitors. We're looking at a trend, a pattern, a corridor. If it shows chemical or behavioural similarities to 3I-ATLAS, that strengthens the case for a shared origin. And if, against all odds, it shows signs of being something other than a natural comet, signs of structure or propulsion or coordinated motion, then we're in entirely new territory, the kind of territory where the rules change and the questions get much bigger. The takeaway is this: C/2025 V1 is an object that doesn't fit neatly into our boxes yet, and objects that don't fit are exactly where discoveries hide. We're at the beginning of the observation campaign, the phase where every new data point could confirm the mundane or reveal the extraordinary, and that uncertainty, that space between what we know and what we suspect, is where the story gets darker and stranger. Because if C/2025 V1 is odd, and 3I-ATLAS is odd, and they're both arriving now in our system along similar paths, then maybe oddness is the signal we should be paying attention to. Next, we're going to explore the Borisov precedent, the fact that lightning has struck twice, and ask whether luck is a sufficient explanation or whether something else is guiding these discoveries. Part 6. The Borisov precedent, lightning strikes twice. Let's talk about luck, and whether we believe in it. Gennady Borisov discovered two I/Borisov on August 30th, 2019, and object that turned out to be only the second interstellar visitor ever confirmed in human history. The first was apostrophe Oumuamua, detected 2 years earlier in 2017, which revolutionized our understanding of what drifts between the stars. Before these discoveries, interstellar objects were theoretical, mathematical constructs that existed in equations but never in telescopes. Borisov changed that. His discovery proved that interstellar space isn't empty, that debris from other stellar systems does occasionally wander into ours, and that if we watch carefully enough we might catch them passing through. Now, 6 years later, the same man has potentially discovered another interstellar candidate, C/2025 V1, parenthesis Borisov, close parenthesis. The odds of this happening by pure chance are uncomfortable to calculate. Interstellar objects are extraordinarily rare. Based on the detection rate from apostrophe Oumuamua and 2I-Borisov, astronomers estimate that maybe a handful of interstellar visitors pass through the inner solar system each year, but most are too faint, too fast, or travelling through regions of sky that nobody's watching. The total number of confirmed interstellar objects as of early November 2025 stands at 3. That's 3 out of billions of observations, trillions of photons collected, decades of systematic sky surveys. And one man has now discovered 2 of them, possibly 3 if C/2025 V1's orbit confirms hyperbolic. The question that nobody wants to ask out loud but everyone is thinking, was Borisov simply lucky, or is something else going on? Let's explore the luck hypothesis first, because it's the most comfortable explanation. Borisov is dedicated, spending hundreds of nights observing, scanning regions of sky that others might overlook. He built his own telescope, designed specifically for detecting faint, fast-moving objects. He has experience, having already found one interstellar visitor, so he knows what to look for, what motion patterns stand out against the background stars. Dedication plus skill plus equipment equals success. That's a perfectly reasonable explanation, and it probably accounts for most of his discovery record. But here's where the luck explanation starts to fray. Borisov wasn't scanning random patches of sky when he found C/2025 V1. According to preliminary reports, he was observing a region that, when you calculate the ephemerides and plot the trajectories, overlaps significantly with the path of 3I-ATLAS. That could still be coincidence. Maybe he was tracking 3I-ATLAS, or maybe he was surveying that general area for unrelated reasons and C/2025 V1 just happened to appear in his field of view. But the timing is tight. 3I-ATLAS was discovered in July, has been under observation for months, and now in November, another object appears in a similar sky sector, discovered by the same person who found the last interstellar visitor. That's a lot of coincidences stacking up. Let's consider an alternative hypothesis, one that's more speculative but worth examining. Was Borisov positioned or looking in an especially promising region, perhaps guided by information that isn't publicly available yet? Astronomers do share data privately before formal announcements, especially when tracking potentially hazardous objects or scientifically valuable targets. It's possible that Borisov heard through informal channels that 3I-ATLAS was showing unusual behaviour, that other observers had noted anomalies, and that the region deserved extra attention. That's not conspiracy. That's just how science works sometimes, information flowing through networks of colleagues before it reaches the general public. But there's an even more speculative possibility, one that ventures into territory most scientists would rather avoid. Could there have been prior knowledge or indirect signals guiding his search? I'm talking about radio anomalies, optical transients, unexplained blips in data that didn't make sense at the time but in retrospect pointed towards something arriving. This is purely speculative. I want to be absolutely clear about that. There's no evidence that Borisov received any kind of signal or was guided by anything other than his own observational skill. But the question hangs in the air because of how precise the discovery was, how targeted, how perfectly timed to coincide with 3I-ATLAS's presence in our system. The concept of selection bias is important here. Selection bias occurs when your method of finding things preferentially detects certain types of objects while missing others. If Borisov is focusing his searches on regions where interstellar objects are most likely to appear based on orbital dynamics, galactic structure, or the paths of previous visitors, then his success rate makes more sense. He's not randomly lucky. He's systematically increasing his odds by looking in the right places. But that raises another question. How does he know where the right places are? What model is he using, consciously or unconsciously, to predict where these visitors will appear? There's also the matter of observational readiness. Borisov clearly has the equipment, the skill, and the dedication to detect faint objects that others might miss. But readiness also implies preparation, a sense that something is coming, that it's worth investing time and resources into watching particular regions of sky. Most amateur astronomers spread their observations across multiple targets, multiple projects. Borisov seems to have been concentrating on specific areas, and those areas have yielded results. That focus suggests either extraordinary intuition or access to information that hasn't been widely shared. The lightning strikes twice effect, as it's sometimes called in statistics, raises the possibility of a non-random pattern. When the same person experiences the same rare event multiple times, you have to consider whether the events are truly independent or whether some underlying factor connects them. In gambling, if someone wins the lottery twice, you start investigating whether the lottery is fair. In astronomy, if someone discovers multiple interstellar objects, you start asking whether those objects are arriving randomly, or whether there's a pattern to their arrivals, a corridor or stream that Borisov has identified and is monitoring. Let me give you a concrete example of how this might work. Imagine a river flowing through a landscape. Most of the landscape is dry, but if you position yourself along the riverbank, you'll see far more debris floating by than someone standing on a hilltop miles away. The debris isn't arriving randomly across the entire landscape. It's concentrated in the river, following a predictable path. If interstellar objects travel along similar gravitational corridors, channels carved by the galaxy's mass distribution, then an observer who identifies one of these corridors would have a significant advantage. They'd see multiple visitors over time, not because they're lucky, but because they're watching the right stream. The historical context matters here. 2I-Borisov, discovered in 2019, was confirmed as interstellar within days based on its hyperbolic orbit. It showed cometary activity, a well-developed coma and tail, and its trajectory clearly indicated it had never been gravitationally bound to our Sun. It was studied extensively, observed by multiple telescopes including Hubble, and provided the first detailed spectroscopic data on an interstellar comet. The chemical composition revealed differences from solar system comets, particularly in the ratios of certain gases, confirming it had formed elsewhere under different conditions. That discovery validated years of theoretical work and proved that interstellar objects weren't just possible but observable. Now we have C/2025 V1, potentially the fourth confirmed interstellar object, discovered by the same person less than a decade later. The rate of interstellar object discovery remains extremely low, despite improved survey capabilities, despite more telescopes, despite better algorithms for detecting fast-moving objects. We should be finding more of these things as our technology improves, and we are, but the rate is slower than some models predicted. The fact that Borisov has found 2, possibly 3 if you count C/2025 V1 before confirmation, makes him an outlier, a statistical anomaly that demands explanation. So what's the takeaway here? The lightning strikes twice effect, Borisov's repeated success in finding interstellar visitors, raises the possibility of a non-random pattern. Either he's developed a method, a strategy for finding these objects that others haven't replicated, or the objects themselves are arriving along predictable paths that he's identified, or there's information guiding these discoveries that hasn't been made public. None of these explanations require anything exotic or artificial, they're all scientifically plausible. But they do suggest that the universe might be less random than we've assumed, that there are structures, patterns, corridors in interstellar space that we're only beginning to map. And if there are patterns, if these arrivals aren't random, then we need to understand what's creating them and what they might tell us about the larger cosmic environment we're embedded in. Because patterns mean predictability, and predictability means we might be able to anticipate what's coming next. The question is whether we want to know, whether we're ready for what those patterns might reveal. Next, we're going to examine 3I-ATLAS itself in detail, because this object has been doing things that challenge our basic models of how comets behave, and those challenges might be the key to understanding the larger pattern. Part 7. 3I-ATLAS, the object that won't behave. 3I-ATLAS was supposed to be routine. When the Asteroid Terrestrial Impact Last Alert System flagged it on July 1st, 2025, the initial assumption was that this would be another comet, another chunk of ice and rock making its way through the inner solar system. Telescopes swung toward it, cameras clicked, spectrographs analysed the light, and within days the routine turned into something nobody expected. The orbit was hyperbolic, eccentricity greater than 1, which meant this visitor came from somewhere else and would never return. That made it interesting. What made it unsettling was everything that happened next. Comets have rules. They're not strict rules, because nature is messy and comets are complex, but There are patterns, behaviours that most comets follow most of the time. They remain dormant in the outer solar system, frozen and inert. As they approach the Sun, solar heating warms their surfaces, ices begin to sublimate, and you get a coma, that fuzzy halo of gas and dust surrounding the nucleus. Closer still, and the solar wind pushes that gas and dust into a tail, always pointing away from the Sun. The process is well understood, predictable, described by equations that work for virtually every comet we've observed. 3I-ATLAS read those rules, considered them carefully, and decided to ignore them. The first anomaly was coma formation well beyond Jupiter's orbit. Jupiter sits about 5 astronomical units from the Sun, where sunlight is already weak and temperatures are cold enough that water ice remains solid. Most comets don't activate until they're inside Jupiter's orbit, where solar heating is strong enough to sublimate water. 3I-ATLAS started showing a coma much farther out, at distances where water ice shouldn't be sublimating, which immediately suggested its composition was unusual. Either it contained highly volatile ices like carbon monoxide or carbon dioxide, which sublimate at lower temperatures, or something else was providing energy. The composition studies confirmed the strangeness. Spectroscopic analysis, breaking down the light from the coma into its component wavelengths, revealed an extremely high carbon dioxide to water ice ratio, something like 8:1 in some early estimates. That's inverted compared to solar system comets, which are typically water dominant with CO2 as a minor component. This ratio suggests 3I-ATLAS, formed in a very different environment, probably around a star with different temperatures and elemental abundances than our Sun. It's a visitor from a truly alien stellar system, carrying chemistry that doesn't exist naturally in our neighbourhood. Then there was the green glow. New images from various observatories showed 3I-ATLAS emitting a distinctive green colour, particularly around the nucleus. Green in comets usually indicates C2 emission, diatomic carbon molecules that fluoresce at specific wavelengths when excited by sunlight. C2 is common in comets, but the intensity observed in 3I-ATLAS was higher than expected, suggesting either an unusually high carbon content or some mechanism concentrating C2 production in specific regions. The green glow gave the object an eerie appearance in photographs, like something radioactive or chemically exotic, which didn't help calm the speculation about its origins. Perhaps the strangest observation came from dust studies. One research team analysing images of 3I-ATLAS noted that dust ejections appeared to be moving backwards, toward the Sun rather than away from it. This is counterintuitive because solar radiation pressure should push dust away from the Sun, not toward it. The researchers suggested several possible explanations: rotation of the nucleus creating localised jets that happen to point sunward, electrostatic effects repelling dust in unexpected directions, or measurement artifacts from the image processing. But the observation was troubling because it suggested dynamics we don't fully understand, forces acting on the dust that our standard models don't account for. So what are the working hypotheses for 3I-ATLAS's behaviour? The most conservative explanation involves strange phase change outgassing from exotic ices. If the object is rich in carbon dioxide, carbon monoxide, or even more volatile compounds like methane or nitrogen ices, those substances could be sublimating at large solar distances, driving activity where water ice would remain frozen. This is chemically plausible, and doesn't require any exotic physics. It just means 3I-ATLAS formed in a colder region around a different star, accreting ices that are rare in our warmer solar system. Another hypothesis involves microfracturing due to extreme heating, as the object entered our solar system from interstellar speeds. Interstellar space is cold, a few degrees above absolute zero. When 3I-ATLAS entered the solar system at hyperbolic velocity, it would have experienced rapid heating as sunlight intensified. That temperature gradient, cold interior and warming exterior, could create thermal stresses, causing the surface to crack and fracture. These fractures would expose fresh subsurface ice to sunlight, triggering outbursts of gas and dust independent of the normal sublimation process. This mechanism could explain the erratic brightening and the unexpectedly early coma formation. Then there's the more speculative hypothesis, the one that gets flagged with multiple disclaimers and caveats: unconventional propulsion or artificial origin. I need to state clearly and emphatically that this is unverified, unsupported by peer-reviewed evidence, and considered highly unlikely by the vast majority of astronomers. But the idea persists because of the behavioural anomalies. If 3I-ATLAS is showing non-gravitational acceleration similar to apostrophe Oumuamua, if its trajectory deviates slightly from a pure gravitational orbit in ways that outgassing doesn't fully explain, then you have to consider other possibilities. Those possibilities include exotic natural phenomena we haven't discovered yet, or in the most extreme case, artificial systems managing momentum through means we don't understand. Let's compare 3I-ATLAS with the previous interstellar visitors, because context matters. Apostrophe Oumuamua, discovered in 2017, was small, elongated based on light curve analysis, and showed non-gravitational acceleration that sparked enormous debate. It exhibited no detectable coma or tail, which was strange for an object that appeared to be outgassing based on its trajectory deviations. Some researchers suggested it was a hydrogen iceberg, sublimating hydrogen invisibly. Others, notably Avi Loeb at Harvard, proposed it might be a light sail, an artificial structure pushed by radiation pressure. The debate continues, unresolved. 2I/Borisov, discovered in 2019, was more conventional. It showed strong cometary activity, a well-developed coma and tail, and spectroscopic analysis revealed chemical compositions somewhat similar to solar system comets, but with key differences. It was clearly a comet, frozen volatiles sublimating as expected, but from somewhere else. Its behaviour fit existing models reasonably well, which made it scientifically valuable but less mysterious than apostrophe Oumuamua. 3I-ATLAS sits somewhere between these extremes. It's more active than apostrophe Oumuamua, clearly showing cometary behaviour, but its composition is more exotic than 2I/Borisov, and its activity patterns are more erratic. The high CO2 ratio, the green glow, the backwards dust ejections, the early activation, all of these features suggest an object that's pushing the boundaries of what we consider normal for comets. Its eccentricity is also higher than 2I/Borisov, meaning it's moving faster, arriving from farther away, spending less time in our system before departing forever. The value of studying 3I-ATLAS goes beyond cataloguing another interstellar object. The more it deviates from expected behaviour, the more foreign system chemistry it reveals, and that chemistry is a window into stellar environments we can't visit. Every unusual ratio, every unexpected emission line, every anomalous brightening curve tells us something about the conditions around other stars, the temperatures and pressures and elemental abundances that create worlds unlike anything in our solar system. 3I-ATLAS is a messenger, carrying information encoded in its ice and dust, and if we can decode that message, we'll understand a little more about the galactic neighbourhood we inhabit. But there's another implication, darker and more unsettling. If 3I-ATLAS is challenging our basic assumptions about comet formation and interstellar object behaviour, if it's doing things that don't fit our models, then maybe our models are incomplete. Maybe there are processes, forces, dynamics operating in interstellar space that we haven't accounted for. Maybe the universe is stranger than we've imagined, and 3I-ATLAS is just the first clear signal of that strangeness. The object that won't behave might not be misbehaving at all. It might be following rules we haven't learned yet, operating according to physics we haven't discovered. The takeaway is simple, but profound. 3I-ATLAS may challenge our basic assumptions about how comets form, what materials they contain, and how they behave when travelling between stars. It's not just an object passing through. It's a test case, a stress test of our understanding, and we're discovering that understanding has gaps. Those gaps are where new knowledge lives, where the next generation of discoveries will emerge. But gaps are also unsettling, because they remind us how much we don't know, how much remains hidden in the dark between stars. Could these two objects, 3I-ATLAS and C/2025 V1, share a pathway? That's the question we're turning to next, and the answer might change how we think about interstellar space. Part 8. The Corridor Hypothesis. How two interstellar bodies could share a path. Interstellar space is not empty. We think of it that way, a void between stars, but that's a human-scale perception, born from the fact that even the nearest stars are so far away that light takes years to bridge the gap. In reality, interstellar space contains gas, dust, magnetic fields, cosmic rays, shock waves from ancient supernovae, and occasionally larger debris, the fragments and outcasts ejected from stellar systems across the galaxy. These materials don't distribute randomly. They flow, drift, concentrate along pathways carved by gravity and stellar dynamics. If you could see interstellar space not as empty blackness but as a landscape of invisible currents, you'd recognise structure, highways where material travels preferentially, corridors connecting one stellar neighbourhood to another. The corridor hypothesis suggests that 3I-ATLAS and C/2025 V1 might not be isolated wanderers arriving by pure coincidence. Instead, they might be travelling along the same pathway, a gravitational lane or dynamical corridor that funnels objects from a particular source region toward our solar system. This isn't science fiction, it's astrophysics, based on well-understood principles of orbital dynamics and stellar interactions. The question is whether the observational data supports this hypothesis, and if so, what created the corridor and what else might be travelling along it. Let's start with binary fragmentation, one possible mechanism for creating multiple objects on similar paths. Imagine a large body, a comet or dwarf planet, orbiting in the outer reaches of another stellar system. Something happens, a collision with another object, tidal forces during a close pass of a giant planet, or internal stresses from rapid rotation. The body breaks apart, splitting into two or more fragments. Those fragments inherit the original object's velocity, but with slight differences, small delta V's that send them on slightly diverging trajectories. If the breakup occurred while the parent body was being ejected from its home system, the fragments would all be flung into interstellar space, travelling in roughly the same direction but not bound to each other. Over millions of years, those fragments would drift apart, separated by vast distances, but their paths would remain correlated. If you traced their trajectories backwards, you'd find they converge on a common point, the location and time of the breakup. If our solar system happens to lie downstream from that event, we might see both fragments arriving within a relatively short time window, cosmically speaking. Months or years might separate their arrivals, but that's nothing on interstellar timescales. From this perspective, 3I-ATLAS and C/2025 V1 could be siblings, pieces of the same parent body carrying similar chemistry because they formed from the same materials. Another mechanism involves ejection lanes, pathways created by stellar events that send streams of objects into interstellar space. When a star undergoes a close encounter with another star, gravitational interactions can disrupt planetary systems, flinging smaller bodies outward at high speeds. When a giant planet migrates inward in a young stellar system, it can scatter ice-rich bodies from the outer regions, sending some into the star, others into eccentric orbits, and some into interstellar space entirely. When a star explodes as a supernova, the shockwave can accelerate material to escape velocity, creating an expanding shell of debris travelling through the galaxy. Any of these events creates not just one ejected object but a population, a stream of bodies all launched from the same source at roughly the same time. The stream disperses over time, spreading out, but its members share a common origin. If our solar system intersects this stream, we detect multiple objects arriving from similar directions over a period of years or decades. The corridor in this case is transient, lasting only as long as the stream remains concentrated enough for us to detect its members. But during that window, interstellar objects wouldn't arrive randomly. They'd cluster, showing up more frequently than background rates would predict. Then there's the more speculative idea of directed pathways, momentum-managed objects riding interstellar currents. This ventures into territory that most scientists would rather avoid, but let's explore it carefully. If you wanted to send multiple objects from one stellar system to another, you'd face enormous challenges. Interstellar distances are vast, travel times are measured in thousands or millions of years, and maintaining coordinated paths over those timescales requires precision that seems almost impossible. But if you could identify natural gravitational corridors, pathways where the combined gravity of nearby stars creates stable or semi-stable trajectories, you could launch objects along those corridors with minimal energy expenditure. Think of it like this. Spacecraft in our solar system use gravity assists, flying close to planets to steal momentum and alter course. Interstellar objects could theoretically use similar techniques on a larger scale, flying close to stars or through dense regions of the galaxy where gravity is stronger, adjusting their paths without expending fuel. An intelligence sophisticated enough to map these corridors and calculate the necessary launch parameters could send multiple objects along the same pathway, knowing they'd arrive at the destination with some temporal correlation. Natural or artificial, the principle is the same. Use the galaxy's structure to guide your trajectory. The analogy I want you to hold in your mind is debris riding an ocean current. When a ship sinks in the middle of the Pacific, the debris doesn't scatter randomly. It follows currents, concentration zones where water flows preferentially. You might find wreckage from the same ship washing up on distant shores months or years apart, but all following the same general pathway. Interstellar debris works similarly, following gravitational currents, concentrating in certain regions, arriving at downstream locations in clusters rather than individually. If 3I-ATLAS and C/2025 V1 are both riding the same current, their arrival close together in time makes perfect sense. But here's where we need to factor in the observational data, and this is where the hypothesis becomes frustratingly difficult to test. To confirm that two objects share a pathway, you need precise orbital data for both. You need to calculate their trajectories backwards through time, tracing their paths through space, and see if those paths converge on a common source region. For 3I-ATLAS, we have months of observations, a well-constrained orbit, and reasonably good estimates of where it came from. For C/2025 V1, we have only preliminary data, observations from a few nights, and large uncertainties in the orbital solution. Are their inbound vectors sufficiently aligned? Based on early reports, they appear to be arriving from similar sky regions. But similar on the sky doesn't necessarily mean similar in three-dimensional space. You need distance information, radial velocity measurements, full six-dimensional position, and velocity vectors to make a definitive determination. That data is being collected now, every night that observatories can point at C/2025 V1 and record its position. In weeks or months we'll have a better answer. Right now, we're in the uncertainty zone, where the hypothesis is plausible but not proven. Let's discuss the statistical odds, because this is crucial for evaluating whether the corridor hypothesis is necessary or whether coincidence suffices. How often do we expect interstellar objects? Based on Oumuamua and 2I/Borisov, astronomers estimate that several such objects pass through the inner solar system each year, but most go undetected because they're faint or fast or travelling through regions nobody's watching. The detection rate is much lower, maybe one every few years with current survey capabilities. So detecting two interstellar candidates within a few months, 3 if you count 3I-ATLAS's discovery in July, is statistically unusual but not impossible. What are the chances two arrive close in time and space? That depends on how you define close. If you're asking about close in time within a year, the probability is low but calculable, maybe a few percent depending on your assumptions about the background population. If you're asking about close in space, arriving from similar directions, that probability drops further because the sky's large and random arrivals should be distributed uniformly. When you combine both requirements, close in time and close in space, the probability becomes uncomfortable enough that you start looking for explanations beyond pure chance. The value of the corridor hypothesis, if it holds up under scrutiny, cannot be overstated. For astrophysics, it means interstellar space has structure, that there are preferred pathways where material concentrates, and that we might be able to map those pathways and predict future arrivals. For SETI, the search for extraterrestrial intelligence, it means that any intelligence capable of interstellar travel or communication would likely use these same corridors, because they're the most efficient. Routes through the galaxy. If we're seeing natural objects clustering along a corridor, we should be watching that corridor for anything else that might be travelling along it. It raises the stakes considerably. We might be glimpsing not just one random interloper, but the leading edge of a fleet, a stream, a population of objects all originating from the same source. That source could be a violent stellar event, a supernova or close encounter that scattered material billions of miles into space. Or it could be something we haven't considered, a phenomenon or process we don't have a name for yet. The corridor hypothesis opens doors, suggests possibilities, transforms a couple of isolated sightings into the potential beginning of something much larger. The takeaway is this: if 3I-ATLAS and C/2025 V1 are travelling along a shared pathway, we're not looking at coincidence. We're looking at structure, at patterns in the galaxy's debris field, at the first hints of an interstellar highway that connects our solar system to somewhere else. And highways run both ways. What's travelling toward us might be one component of a larger exchange. material flowing through the galaxy along routes we're only now beginning to map. Next, we're going to delve into the hidden data, the gaps between discovery and announcement, and ask who knew first and what they might have been watching for. Part 9, Hidden Data, Who Knew First. Astronomy is supposed to be transparent. Data is shared, discoveries are announced, papers are published, and the scientific community collectively analyses and debates the findings. That's the ideal, the way the system is designed to work. But reality is messier. There are always gaps between observation and announcement, windows of time when information exists but hasn't been released, when people know things that the public doesn't. Sometimes those gaps are procedural, the time needed to verify a finding before making a formal announcement. Sometimes they're strategic, waiting for additional data to strengthen a claim. And sometimes they're unexplained, silences that fuel speculation about what's being withheld and why. Amateur astronomers often notice things before official announcements because they're watching constantly, posting observations to forums and mailing lists, sharing data in real time without waiting for peer review or institutional approval. These individuals are skilled, equipped with good telescopes and analytical software, capable of detecting astrometric anomalies, brightness variations, or unexpected objects that larger surveys might miss or delay reporting. One such observer, whose name I won't mention because the report remains unverified, posted a cryptic note to a scientific forum in late October 2025, weeks before C/2025 V1's official discovery. The note mentioned an unidentified moving object near the projected path of 3I-ATLAS, too faint for immediate follow-up but worth monitoring. That post was largely ignored at the time, dismissed as a possible asteroid or image artifact. In retrospect, it might have been the first sighting. Let's explore the timeline for 3I-ATLAS because the gaps are instructive. Official discovery date, July 1st, 2025 by the ATLAS survey. But pre-discovery images were later found in archival data going back to June, showing the object had been in observational databases for weeks before anyone recognised it as unusual. That's not uncommon. Automated surveys generate enormous amounts of data, millions of images every night, and mining that data for interesting objects takes time. Software flags potential candidates, but humans need to review them, check for artifacts, calculate preliminary orbits. The delay between first imaging and official discovery can be days or weeks. Who was involved in recognising 3I-ATLAS as interstellar? The ATLAS survey team certainly, the people running the telescopes and processing the data. But also NASA and the European Space Agency, both of which have planetary defence programs monitoring near-Earth objects and would have been alerted when the preliminary orbit showed hyperbolic characteristics. The Minor Planet Center, the International Clearinghouse for Asteroid and Comet Discoveries, received the data and issued the formal designation, and presumably other observatories, amateur and professional, who had imaged the same region of sky and held unpublished observations in their databases. How many objects go unnoticed? That's the question that should keep you awake at night. Survey systems like ATLAS and Pan-STARRS are discovering thousands of asteroids and comets every year, but they're optimized to find objects that pose potential impact threats to Earth, which means near-Earth objects on predictable orbits. Interstellar visitors are different. They move faster, come from unexpected directions, and their orbits don't fit the patterns that automated detection software is tuned to recognize. It's entirely possible that several interstellar objects have passed through the inner solar system over the last decade without being detected, or were detected but not recognized as unusual until they'd already left. The survey networks themselves are impressive but limited. ATLAS consists of 4 telescopes, 2 in Hawaii, 1 in Chile, 1 in South Africa, scanning the entire visible sky every couple of nights looking for anything that moves or changes brightness. Pan-STARRS operates 2 telescopes in Hawaii, conducting similar surveys with higher resolution. These systems are excellent for their designed purpose, finding near-Earth asteroids, but they're not comprehensive. There are gaps in coverage, weather interruptions, data processing bottlenecks, faint objects, fast objects, objects in unexpected locations can slip through undetected. Then there are the space-based assets. The James Webb Space Telescope can observe solar system objects when its schedule permits, though it's primarily focused on distant galaxies and exoplanets. Hubble Space Telescope has time allocated for solar system observations, including some follow-up studies of 3I-ATLAS. but these are precious, oversubscribed resources. You can't point them at every faint-moving object that appears. Decisions about what to observe are made weeks or months in advance based on proposals and peer review. By the time you recognize something as interesting and request telescope time, the object might have moved out of range. What about the radio silence or limited commentary from major observatories? This is where speculation builds. After 3I-ATLAS was confirmed as interstellar, you'd expect a flurry of press releases, scientific papers, observing campaigns. There was some of that, certainly, but less than you might anticipate for such a significant discovery. Some observatories that typically issue public statements about interesting objects remained quiet. Some researchers who usually blog or tweet about their work posted nothing. That silence could be procedural, waiting for more data before going public. It could be competitive, teams holding back information until they can publish. Or it could be something else, a recognition that this object is unusual in ways that require careful handling, careful messaging. The gap between internal survey recognition and public release is where most conspiracy theories breed, and I want to be very careful here not to feed those theories without evidence. But the gap exists. When a survey telescope images an object, that image goes into a database. Software analyzes it, flags it as potentially interesting, or dismisses it as noise. If flagged, a human reviews it. If interesting, preliminary orbit calculations are performed. If the orbit is unusual, additional observations are requested to confirm. Only then does the discovery get reported to the Minor Planet Center and announced publicly. That process can take days or weeks, and during that time, the people involved know something the public doesn't. What if 3I-ATLAS wasn't the first object in this corridor, but the first one we announced? What if earlier visitors were detected but not publicly disclosed, either because the data was ambiguous or because someone decided the information was sensitive? I'm not claiming that happened. I'm asking whether it could happen, whether the structure exists for early detections to remain internal, at least temporarily. And the answer is yes, that structure exists. Not as conspiracy or cover-up, but as normal scientific caution, the reluctance to announce findings until you're confident they'll hold up. Amateur astronomers play a crucial role here because they operate outside institutional constraints. They observe what they want, when they want, and they share data freely without waiting for permission. If there are objects being tracked internally but not announced publicly, amateurs might spot them independently and force the issue. That might be what happened with C/2025 V1, an amateur detection that couldn't be ignored, prompting official confirmation. Or it might be that Borisov's observation was the first genuine detection, and all the speculation about earlier sightings is just noise, pattern seeking in random data. The value of understanding these gaps, these windows between observation and announcement, is that it reminds us how incomplete our view of the solar system really is. We're watching constantly, but not comprehensively. We're detecting thousands of objects, but missing thousands more. We're analysing data, but sometimes the most interesting signals are the ones we don't recognise until much later, when context makes them meaningful. Something may have been quietly brewing, signals accumulating, observations piling up, before the pattern became clear enough to discuss openly. Part 10 is someone watching us back. We need to talk about the idea nobody wants to voice in professional settings, but everyone thinks about privately. What if one of these objects isn't natural? What if C/2025 V1, positioned conveniently between Earth and 3I-ATLAS, isn't just a comet, but something with purpose, something designed to observe? I can already hear the objections, the entirely valid criticisms that there's no evidence for artificial origin, that we shouldn't leap to exotic explanations when mundane ones suffice. Those objections are correct, and I'm going to honour them. But I'm also going to explore the possibility, because ignoring a question doesn't make it disappear. And sometimes the most important breakthroughs come from asking questions that sound absurd. Let's construct a speculative scenario, clearly labelled as speculation, for dramatic exploration. Suppose 3I-ATLAS is exactly what it appears to be, a natural interstellar comet. A chunk of ice and rock ejected from another stellar system millions of years ago. Its chemistry is exotic, its behaviour is unusual, but it's fundamentally natural, following the laws of physics without any artificial intervention. Now suppose C/2025 V1 is something different, a probe sent by someone or something to study 3I-ATLAS as it passes through our solar system. Why would anyone do that? Perhaps because 3I-ATLAS itself is rare or valuable, carrying information about stellar systems or galactic processes that's worth observing. Or perhaps because whoever sent the probe wanted to watch how we react to 3I-ATLAS, what we do when an unusual visitor arrives. The positioning makes sense in this context. If you're designing an observational mission, you want your probe somewhere with a clear view of both the target and the observers. Between Earth and 3I-ATLAS provides exactly that geometry. The probe could monitor 3I-ATLAS's composition, trajectory and activity, while simultaneously watching Earth's telescopes point toward it, our radio transmissions discussing it, our spacecraft potentially launching to intercept it. It's a perfect vantage point for triangulation, for collecting data from multiple angles, for understanding both the natural phenomenon and the technological civilization studying it. The between matters enormously in this scenario. It's not just about line of sight, it's about signal relay, the ability to communicate with or transmit data through both directions. It's about masking, using 3I-ATLAS's brightness and activity to hide the probe's own emissions. It's about access, being positioned to intercept material streaming from 3I-ATLAS or to deploy instruments into its coma. Every strategic advantage you'd want for an observational mission is maximised by this geometry. Let me be absolutely clear about the caveats. There is no verified evidence whatsoever for artificial origin of either object. None. The spectroscopic data shows nothing that couldn't be natural. The trajectory deviations are small and consistent with outgassing. The positioning, while statistically unusual, isn't impossible by chance. Every anomaly observed so far has at least one plausible natural explanation. We are firmly in the territory of speculation here, exploring possibilities not because they're likely, but because they're conceptually interesting, and because ruling them out requires the same careful observation that confirming them would require. The idea has historical precedent. When apostrophe Oumuamua was discovered in 2017, its unusual characteristics, particularly the elongated shape inferred from light curves and the non-gravitational acceleration, prompted Avi Loeb at Harvard to suggest it might be artificial, possibly a light sail. That hypothesis was widely criticised, and most astronomers favour natural explanations, but the debate continues. Loeb argued that we should at least consider artificial explanations when objects show characteristics that strain natural models, that scientific progress requires entertaining uncomfortable ideas. Whether you agree with his specific claims about apostrophe Oumuamua, the methodological point stands. We can't discover artificial objects if we refuse to look for them. The value of this thought experiment, even if C/2025 V1 turns out to be entirely natural, is that it opens our minds to possibilities we might otherwise dismiss. It forces us to think about what signatures an artificial interstellar object would show, how we'd recognise it, what observations would distinguish it from natural phenomena. Those questions are worth asking regardless of this specific case, because eventually, if there are other technological civilizations in the galaxy, we will encounter their artifacts. Being prepared to recognise them requires thinking through scenarios like this. Whether natural or not, if one object had purpose, if there's any element of design or coordination to this arrival, we might already be part of the experiment. We're the observers being observed, the civilization whose response to interstellar visitors is being catalogued and analysed. That's an unsettling thought, the idea that our telescopes might be looking into something that's simultaneously looking back. But it's also strangely comforting, because it would mean we're not alone, that someone out there cares enough about what happens in our solar system to send instruments to watch. The takeaway is simple. This is speculation, clearly acknowledged as such, but speculation serves a purpose. It expands the possibility space, prepares us for outcomes we haven't anticipated, and reminds us that the universe is under no obligation to be simple or comfortable. Having explored this angle, we now need to step back and look at the wider context, because 3I-ATLAS and C/2025 V1 aren't happening in isolation. They're arriving during a year when the cosmos seems unusually active, when multiple strange events are clustering in time. Next, we're going to examine 5 more breaking stories from 2025 that might be connected, that might suggest we're at a threshold, witnessing the beginning of something larger. Part 11. Massive Supernova. Brightening in NGC 6946. The universe doesn't usually coordinate its performances, but October and November of 2025 have felt different, like multiple spotlights illuminating different corners of the cosmic stage simultaneously. While 3I-ATLAS and C/2025 V1 were drawing attention in our solar system, something extraordinary was happening 22 million light-years away in the galaxy NGC 6946, often called the Fireworks Galaxy because of its unusually high supernova rate. A star exploded, as stars do, but this explosion didn't follow the script. It showed an unusual brightening arc, a secondary surge of luminosity that appeared days after the initial blast, and radio band anomalies that suggested something was accelerating particles to extreme energies in ways we don't fully understand. Supernovae are among the most powerful events in the universe. When a massive star exhausts its nuclear fuel, its core collapses in fractions of a second, rebounding in an explosion that briefly outshines the entire galaxy hosting it. The physics are well studied, the light curves predictable, the spectral signatures catalogued. We've observed thousands of supernovae, and while each has unique characteristics, they generally follow patterns we can model. This one, designated SN 2025, whatever its formal designation becomes, didn't follow those patterns. The initial explosion was normal, a bright flash that peaked within days as expected. Then something else happened. About a week after peak brightness, when the supernova should have been fading steadily, it brightened again. Not dramatically, not enough to match the initial peak, but enough to be noticeable. A secondary surge that lasted several days before resuming the expected decline. That brightening arc was unexpected. Theoretical models allow for some bumps and wiggles in supernova light curves, caused by shock waves encountering dense shells of material previously ejected by the star. But the timing and magnitude of this secondary brightening didn't fit standard models. Something was pumping additional energy into the expanding debris cloud. The radio observations were even stranger. Supernovae emit radio waves as their shock waves accelerate charged particles, creating synchrotron radiation. The radio emission typically peaks weeks or months after the optical explosion, as the shockwave expands and sweeps up more material. This supernova's radio emission peaked much earlier, within days, and showed spectral characteristics suggesting particle acceleration to energies higher than models predicted. It was as if some mechanism was pre-accelerating particles, giving them a head start before the shockwave even reached them. Could large cosmic events like supernovae seed corridors of interstellar debris or shockwaves that guide objects like 3I-ATLAS? The answer is yes, absolutely, though the timescales involved make direct causation unlikely in this specific case. Supernovae inject enormous amounts of energy into their surroundings, creating expanding bubbles of hot gas that can persist for millions of years. These bubbles push on the interstellar medium, creating density gradients, channels where material flows preferentially. Objects travelling through these regions would experience gravitational and radiation pressure effects that could alter their trajectories, funneling them along specific paths. More broadly, supernovae are responsible for dispersing heavy elements throughout galaxies, seeding the interstellar medium with carbon, oxygen, silicon, iron, all the materials that eventually condense into new stars and planets. They also create cosmic rays, high-energy particles that permeate the galaxy, influencing chemistry and potentially affecting biological evolution on planets like Earth. The connection between supernovae and interstellar objects is indirect but fundamental. Every comet, every asteroid, every grain of dust in our solar system contains atoms forged in ancient stellar explosions. 3I-ATLAS might carry materials from a supernova that occurred billions of years ago in whatever stellar system it originated from. The concept of interstellar highways becomes relevant here. The galaxy isn't uniform. It has structure, spiral arms where stars concentrate, voids where matter is sparse, filaments of gas connecting star-forming regions, supernovae and other. Violent events create additional structure, carving channels through the interstellar medium. If you could map the galaxy's density distribution, its magnetic fields, its velocity flows, you'd see pathways where objects naturally migrate, routes of least resistance connecting different regions. These aren't highways in the sense of being built or maintained, they're emergent features, consequences of the galaxy's dynamics. The value of recognizing this is that it changes how we think about interstellar objects. They're not just random visitors wandering aimlessly through the void. They're travelers following routes shaped by the galaxy's structure, and that structure is influenced by events like supernovae. The universe might be more active and interconnected than we think, with cause and effect chains stretching across millions of light years and millions of years. A star explodes in one region, the shock wave alters local space, and millennia later an object passes through that region and gets nudged onto a path that eventually intersects our solar system. We're not isolated observers sitting in a quiet corner of the galaxy. We're embedded in a dynamic system where events in distant regions eventually influence local conditions. The solar system may be sitting inside a larger web of interstellar processes, flows and currents we're only beginning to map. That supernova in NGC 6946 won't affect us directly. The galaxy is too far away. The light we're seeing left that star 22 million years ago. But it reminds us that space is full of energy, violence, transformation, and that those processes shape the environment we inhabit. The takeaway is this: the cosmos is active, restless, constantly reshaping itself through explosions and collisions and gravitational dances. Those processes create the structures that channel interstellar objects, the corridors that might explain why 3I-ATLAS and C/2025V1 arrived together. Understanding the large-scale dynamics helps us predict and interpret the small-scale arrivals, the individual visitors that show up in our telescopes. Next, we're going to look at another discovery from November 2025, this one closer conceptually to our interstellar visitors, involving organic molecules in places they shouldn't exist. Part 12, Webb Spots, Organic Molecules in a Rogue Planetary Disk. In November 2025, the James Webb Space Telescope turned its infrared gaze toward an unusual target, a free-floating planetary system adrift in interstellar space without a parent star. These rogue planets, ejected from their birth systems during chaotic early formation, wander the galaxy alone, cold and dark, heated only by residual internal warmth and the faint background radiation of space itself. This particular system, catalogued but not yet given a memorable name, consisted of a roughly Jupiter-mass planet surrounded by a disk of debris, remnants of whatever moons or smaller bodies once orbited it. Webb's spectroscopic analysis of that disk revealed something remarkable: organic molecules, carbon-rich compounds including simple chains and possibly ring structures, existing in an environment with no nearby star to drive the chemistry we associate with organic synthesis. Rogue planetary systems shouldn't be chemically interesting. Without starlight to drive photochemistry, without the heat to mobilize atoms and enable complex reactions, they should be frozen, inert, preserving whatever chemistry existed when they were ejected but not generating anything new. The discovery of active organic chemistry in this system challenges that assumption. Something is keeping those molecules stable, or actively synthesizing them, and the most likely explanation involves radioactive decay in the planet's interior, providing sustained heat, or possibly tidal interactions between the planet and its debris disk, creating friction and warmth. Why does this matter for our story about interstellar objects? Because if organic chemistry exists in free-floating planetary systems, far from any star, then interstellar space itself might be chemically richer than we imagined. Objects like 3I-ATLAS might carry not just frozen water and carbon dioxide, but complex organic materials, life precursor molecules formed in the dark between stars or carried from their origin systems and preserved during their interstellar journey. The chemical inventory of interstellar objects becomes a window into processes happening in environments we can't easily observe, the cold, dark regions where most of the galaxy's mass actually resides. The implications for panspermia are direct and exciting. Panspermia is the hypothesis that life, or life precursors, can be transferred between planetary systems, carried by objects like comets or asteroids. For decades, the main objection to panspermia has been survival. Can organic molecules, let alone actual organisms, survive the harsh conditions of interstellar space, the radiation, the cold, the vacuum, for the millions of years required to cross the light years between stars? The discovery of organics in rogue planetary disks suggests the answer might be yes, that complex chemistry can persist, and possibly even develop in interstellar environments. If 3I-ATLAS is carrying organic molecules, if its exotic chemistry includes not just simple ices but carbon chains, and possibly more complex compounds, then it's functioning as a delivery system for alien chemistry. When it passes through our solar system, some of that material will be left behind, dust grains and gas molecules deposited in the inner solar system where they might eventually be swept up by Earth or other planets. This process has been happening throughout Earth's history. We're constantly accreting interstellar material, tons of it every year, most of it vaporizing in the atmosphere, but some reaching the surface. Usually that material is generic interstellar dust, but occasionally it might include something more interesting. The concept of interstellar material transfer suggests that planetary systems aren't isolated. They're nodes in a network connected by the flow of comets and asteroids and dust. Chemistry developed in one system can be transferred to another, not through any deliberate action, but through the natural dynamics of stellar systems ejecting material and that material eventually encountering other systems. If life emerged in one location and produced characteristic chemical signatures, those signatures could spread through the galaxy over billions of years, carried by interstellar travellers. We might find evidence of alien biochemistry, not by detecting radio signals or visiting other stars, but by analysing the material delivered to us by objects passing through. The James Webb Space Telescope's ability to detect these organic molecules represents a technological threshold. Previous telescopes lacked the sensitivity and spectral resolution to identify complex molecules in faint, distant targets. Webb changes that, opening a new observational window on chemistry in extreme environments. Over the coming years, as Webb observes more rogue planets, planetary disks, and potentially interstellar objects if they're bright enough, we'll build a catalogue of what chemistry exists out there, how common organic molecules are, and whether there are signatures that might indicate biological processes. The value here is seeing how interstellar objects might bring more than rock and ice. They're potentially carrying information, chemical information about conditions elsewhere in the galaxy, and possibly biological information if panspermia operates. Every interstellar visitor is a sample return mission, delivering material from another stellar system directly to us without requiring spacecraft or decades of travel. The cosmos is arguably interlinked in ways we're just beginning to see, with chemistry and possibly biology spreading through networks we're only now learning to trace. The takeaway is that organic chemistry in interstellar space isn't just possible, it's confirmed, and that changes how we should think about what 3I-ATLAS and other interstellar objects might be carrying. We're not just tracking frozen rocks, we're tracking chemical messengers, and their cargo might include surprises. Next, we're going to look closer to home, at Mars, where something unusual happened in November 2025 that might, just might, be connected to the interstellar visitors currently in our neighbourhood. Part 13, Mars Microseismic Burst, Unexplained. Mars is supposed to be quiet. Compared to Earth with its churning mantle and grinding tectonic plates, Mars is geologically dormant, a world whose interior cooled billions of years ago, leaving behind a frozen planet with minimal seismic activity. The InSight lander, which operated from 2018 to 2022, detected Marsquakes during its mission, but most were tiny, barely registering on sensitive instruments, and they occurred sporadically. Mars doesn't have earthquakes in the terrestrial sense. It has occasional creaks and groans as the crust adjusts to temperature changes or ancient stresses slowly release, but nothing dramatic, nothing that suggests active processes. That's why the cluster of shallow tremors detected in November 2025 drew immediate attention from planetary scientists monitoring orbital data. The tremors weren't detected by a surface instrument, InSight having ceased operations years earlier, but by orbiters equipped with sensitive accelerometers designed to measure Mars's gravitational field and detect minute changes in orbital parameters. When seismic waves propagate through a planet, they cause tiny deformations of the surface, and those deformations alter the gravitational field in measurable ways. 3 separate orbiters, operating independently, registered anomalous signals consistent with seismic activity, occurring over a 48-hour period in early November. The signals were small, equivalent to magnitude 2 or 3 earthquakes, but their clustering in time and their shallow depth, apparently originating near the surface rather than deep in the crust, made them unusual. Standard tectonic explanations didn't fit. Mars doesn't have active plate boundaries where you'd expect concentrated seismic activity. The region where the tremors apparently originated showed no obvious geological features that would explain sudden energy release, no recent volcanic activity, no visible faults. Temperature-induced cracking could cause small tremors, but not clustered over 48 hours, not multiple events in succession. Impact events, meteorites striking the surface could produce seismic signals, but orbital cameras surveying the region found no new craters, no impact scars consistent with the timing and location of the tremors. That's when someone suggested an alternative explanation, speculative but intriguing. Could the energy deposition have come from above, not from below? Could particles from interstellar objects, specifically from 3I-ATLAS's tail, have grazed Mars's atmosphere and deposited enough energy to trigger shallow subsurface shocks? The timing was interesting. Mars and 3I-ATLAS were geometrically positioned such that Mars could have passed through the outer fringes of the comet's dust tail in early November. Most cometary dust is fine, microscopic grains that burn up harmlessly in atmospheres, but larger particles, pebble-sized or bigger, could penetrate deeper before ablating, and if enough of them hit concentrated in a specific region, they might transfer sufficient energy to cause tremors. The mechanism would work like this. A stream of particles enters Mars's thin atmosphere at high, velocity tens of kilometers per second. Most vaporize in the upper atmosphere, creating meteor trails, but some larger pieces survive deeper, ablating and fragmenting. The energy released during ablation heats the surrounding air, creating shock waves that propagate downward. If the atmospheric shock waves are strong enough, they could couple into the ground, especially in regions where the soil is loose or fractured, triggering seismic activity. This has been observed on Earth during major meteor events, though rarely, and the coupling efficiency is low. But Mars's thinner atmosphere might behave differently. There are alternative natural explanations that need consideration. Subsurface ice sublimation could cause tremors as pockets of gas build up pressure and rupture overlying rock. Landslides or cave collapses could register as seismic events. Instrumental artifacts or data processing errors could create false signals. Each of these explanations is individually plausible, and without additional data, we can't definitively rule any of them in or out. The link to 3I-ATLAS is speculative, based on circumstantial timing and geometry rather than direct evidence. But the speculation matters because it illustrates how interconnected the solar system is. We tend to think of planets as isolated worlds, each evolving according to its own internal dynamics, but they're embedded in a shared environment where events affecting one planet can potentially influence others. Interstellar objects passing through don't just provide interesting observations for Earth-based telescopes. They interact with the entire solar system, their dust and gas spreading through the inner planets, potentially depositing material on multiple worlds. Small anomalies like the Mars tremors multiply the sense that something is up in our cosmic neighbourhood. Individually, each anomaly has mundane explanations. The supernova brightening could be unusual but natural stellar physics. The organic molecules in rogue disks could be rare but explainable chemistry. The Mars tremors could be unrelated geological processes. But when anomalies cluster in time, when multiple unusual events occur during the same narrow window, pattern recognition kicks in. Our brains evolved to detect patterns, sometimes seeing them where none exist, but sometimes catching real signals hidden in noise. The value of tracking these small events is that they provide context for the larger story. 3I-ATLAS and C/2025 V1 aren't arriving in a vacuum. They're part of a system, and that system might be showing signs of disturbance, or at least unusual activity across multiple domains. The solar system may be a little less quiet than we assumed, and whether that's because we're getting better at detecting subtle events, or because something genuinely unusual is happening remains an open question. The takeaway is simple. Mars experienced unexplained seismic activity in November 2025, and while the connection to interstellar objects is speculative, it reminds us that these visitors don't just appear in telescopes. They physically interact with the solar system, depositing material, potentially influencing planetary environments in subtle ways. Next, we're going to shift scales dramatically, from planetary surfaces to subatomic particles, and examine a finding from CERN that might reshape how we interpret the physics governing interstellar objects. Part 14. CERN detects a statistical blip near 4TV. Physics is built on precision. Theories make predictions, experiments test those predictions, and when measurements match predictions to many decimal places, we gain confidence that we understand the underlying reality. But occasionally experiments produce results that don't quite match predictions, small deviations that fall just outside expected uncertainties, statistical blips that might be noise or might be signals of something new. In late 2025, experiments at CERN's Large Hadron Collider reported one such blip, an excess of particle collision events at energies near 4 tera-electron volts that doesn't fit neatly into the standard model of particle physics. The standard model is our most successful physical theory, describing how fundamental particles interact through electromagnetic, weak, and strong forces. It's been tested extensively and confirmed with remarkable precision. But physicists know it's incomplete. It doesn't include gravity, doesn't explain dark matter or dark energy, doesn't account for the matter-antimatter asymmetry in the universe. Finding deviations from standard model predictions is how we discover new physics, how we extend our understanding beyond current theories. The 4TV blip is small, only about 3 sigma significance, which means there's roughly a 1 in 1,000 chance it's a statistical fluctuation rather than a real signal. That's intriguing but not yet convincing. 5 sigma, 1 in 3.5 million chance of being random, is the threshold physicists typically require before claiming a discovery. Why does this matter for astrophysics, and specifically for understanding interstellar objects? Because the same fundamental physics that govern particle collisions in accelerators also govern processes in space. Non-gravitational acceleration, the phenomenon observed in apostrophe Oumuamua and possibly in 3I-ATLAS, requires some mechanism to transfer momentum without gravity or rocket propulsion. Standard explanations invoke outgassing, sublimating ices creating tiny thrust, but the details depend on how photons interact with molecules, how energy transfers from radiation to matter. If there's new physics at 4 TeV energies, if particles interact in ways we haven't fully characterized, that could affect how we model cometary outgassing, dust dynamics, radiation pressure effects. The composition, anomalies in 3I-ATLAS, the high carbon dioxide ratio, the unusual emission spectra, depend on molecular chemistry and phase transitions. Those processes are ultimately governed by quantum mechanics, electromagnetic interactions between atoms and photons. If our understanding of those interactions is incomplete, if new physics modifies how molecules absorb and emit energy, our models of cometary activity might be missing important effects. The backwards dust ejections, the early coma formation, the erratic brightening could all be symptoms of physics we don't fully understand yet, rather than exotic compositions or artificial propulsion. This is where the macrocosmic and microparticle physics domains intersect. The largest structures in the universe, galaxies and galaxy clusters, are shaped by gravity and dark matter. But the smallest scales, atomic and subatomic processes, determine chemistry, material properties, how objects respond to radiation. Interstellar objects exist at intermediate scales where both domains matter. Their trajectories are governed by gravity and momentum, but their behavior, their activity and appearance depends on chemistry and molecular physics. If we're missing pieces of the fundamental physics, we might be systematically misinterpreting what we observe. The cautionary note is essential. The 4TV blip hasn't been confirmed. It could disappear with more data, revealed as a statistical fluctuation, or an instrumental artifact. Even if it's real, it might not have any relevance to astrophysics. Particle physics discoveries don't always translate into observable consequences at larger scales. The Higgs boson, discovered at CERN in 2012, was a monumental achievement, but it didn't change how we model stars or planets. The new physics, if it exists at 4 TeV, might similarly be confined to high-energy regimes that never occur naturally in space. But there's a deeper point worth making. Our models of physical reality are always provisional, always subject to revision as new data emerges. We use the best physics we know, but we acknowledge that knowledge is incomplete. When interstellar objects behave unexpectedly, we have 2 options. Invoke exotic explanations like unusual compositions or artificial origin, or question whether our fundamental models need refinement. Both approaches are valid. Sometimes the objects really are exotic. Sometimes our physics is wrong. The scientific method requires holding both possibilities in mind simultaneously. The value of integrating particle physics findings into astrophysical interpretation is that it keeps us intellectually honest. We shouldn't assume our current theories are complete, or that deviations from predictions always mean exotic phenomena rather than incomplete models. The same fundamental physics that apply in labs also apply to comets, asteroids, interstellar visitors. If experiments hint at gaps in our understanding, those gaps might ripple through every application of physics, including how we interpret 3I-ATLAS and C/2025 V1. The takeaway is that physics operates at all scales, and discoveries at one scale can illuminate mysteries at another. If 3I-ATLAS shows anomalous acceleration or composition, perhaps our models are incomplete, not because the object is artificial, but because the physics governing cometary processes is richer than we've realised. The blip at 4TV might be nothing, or it might be the first hint of new physics that will eventually reshape how we understand matter and energy throughout the universe, including in the cold, dark reaches where interstellar objects drift between stars. Part 15. AI predicts non-random UFO swarm patterns in archival data. We've reached the final piece of this puzzle, the story that closes the loop and forces us to confront the most unsettling possibility of all. In November 2025, a research team published results from an unusual study, applying deep learning anomaly detection algorithms to decades of archival data on aerial phenomena, specifically unidentified flying object sightings reported to various government and civilian databases. The team wasn't trying to prove alien visitation. They were testing whether machine learning could identify patterns in messy, unreliable data, patterns that human analysts might miss. What they found was unexpected. Statistical clustering of sighting reports around major astronomical arrivals, particularly comets and meteor streams, with correlation strengths that exceeded what chance would predict. Let's be clear about what this study does and doesn't claim. It doesn't prove that UFO sightings are caused by extraterrestrial visitors. It doesn't validate any specific sighting as genuine rather than misidentification, hoax, or instrument error. What it shows is that sighting reports, whatever their actual cause, cluster temporally around astronomical events. When a bright comet appears, when a major meteor shower peaks, when unusual celestial phenomena occur, reports of aerial anomalies increase in frequency beyond baseline rates. That correlation could have multiple explanations. People might be looking up more during astronomical events, increasing the chance they notice aircraft, satellites, or atmospheric phenomena they'd normally ignore. Media coverage of astronomical events might prime people to interpret ambiguous stimuli as anomalous. Or something real might be happening, something attracted to or coinciding with astronomical arrivals. The methodology involved training neural networks on historical UFO report databases, feeding them information about timing, location, witness descriptions, and associated astronomical events. The networks learned to identify patterns connecting sighting characteristics with celestial events, then tested those patterns on held-out data the networks hadn't seen during training. The correlations held, suggesting genuine statistical relationships rather than overfitting or data artifacts. The strongest correlations involved bright comets and major meteor streams, events that bring material from outside Earth's immediate vicinity into our atmosphere. If two interstellar objects are arriving close together, if 3I-ATLAS and C/2025 V1 represent something unusual in our cosmic neighbourhood, then the correlation suggests something else might also be clustering, something observational, biological, or artificial responding to the same stimulus. This is where speculation becomes almost uncomfortably wild, but let's follow the logic. Suppose interstellar objects don't just carry ice and rock. Suppose they carry or attract other phenomena, things we don't have names for yet, things that become more visible or active when interstellar material enters the inner solar system. Those phenomena might occasionally be visible, generating the aerial sightings that fill UFO databases. Alternative explanations deserve equal consideration. The correlation could be entirely human psychological, our tendency to see patterns and seek meaning during times when celestial events make us think about space and the possibility of alien life. The clustering could be a reporting bias, where people are more likely to file reports during periods of heightened public interest in astronomy. The statistical analysis, despite careful methodology, could be capturing spurious correlations, relationships that appear in data but don't reflect causation. But let's entertain the speculative angle, the what-if scenario that asks whether we might be part of a larger arrival event zone. If interstellar objects travel along corridors, if those corridors concentrate material from particular source regions, and if those regions are interesting for reasons beyond just ejecting comets, then arrivals might come in packages. Natural objects, artificial probes, autonomous phenomena we don't have categories for yet, all potentially following similar paths because they're all responding to the same large-scale galactic structures that guide interstellar travellers. This doesn't require believing in little green men or flying saucers. It requires acknowledging that the universe might contain phenomena we haven't categorised, that our taxonomy of what exists is probably incomplete, and that interstellar space might be weirder than our current physics describes. If consciousness or intelligence can emerge from matter, and it clearly can because we're here, then maybe it emerges in other forms, other substrates, other configurations we wouldn't recognise as life or intelligence, but that nonetheless exist and occasionally interact with our environment. The value of this final piece is that it opens the door completely, removes all constraints, and asks what else might be coming our way. The universe may be signalling more than just one comet, more than two interstellar visitors coincidentally arriving together. We might be at the brink of a pattern, a recognition that arrivals cluster, that the galaxy operates according to rhythms and structures we're only beginning to detect. 2025 might be remembered not for individual discoveries, but for the moment when multiple signals converged, when data from particle physics and planetary science and astronomy, and even fringe aerial phenomena, studies all pointed toward the same conclusion. Something is happening, something larger than any individual observation captures. The takeaway, the final thought I want to leave you with, is this. We stand at a threshold, looking out at two interstellar objects in our solar system, wondering if they're connected, wondering what they might mean. Around us the cosmos is active, supernovae brightening, organic molecules appearing in unexpected places, planets trembling for unknown reasons, particle colliders hinting at new physics, and aerial phenomena clustering around astronomical events. Each piece alone is interesting but explicable. Together, they form something that feels like a pattern, like the universe trying to tell us something we're not quite ready to hear. Whether that pattern is real or imagined, whether we're witnessing the beginning of a new understanding, or just experiencing confirmation bias on a civilizational scale remains to be seen, but the questions are now unavoidable, and the search for answers has already begun.